Okay, everybody, let's continue, please. Let's continue, please. We have this expression for our parameter estimate, and I have pointed out that it must be a random variable. We have that here beta is a linear operator, some matrix applied to a random variable. So we can now ask for what is the distribution of beta itself. And we can make weaker or stronger assumptions here. So we can or cannot make the assumption of the residuals being normally distributed. So far I have not made that assumption, right? But so far we have found is the mean of the distribution describing our parameter estimate. I'm writing here in short, we have found the mean of the random variable beta. And if we want to know more about the distribution, the next thing after knowing the mean is to know about its covariance structure. Yeah, so the second moment. So we want to find out about the covariance of beta. And the only random variable that we really have in there, so beta depends on y, but y itself had a deterministic term and a random term, and the random term was this epsilon, this noise term. So we found out what beta is. It's x transpose to the -1 times x times y transpose. We check that this is what we had. Yes. And remember, what was this y itself? So I'm just copying. But now the y itself was made up of, on the one hand, the linear model itself, so this was x transpose times the true parameter beta, I think we wrote beta star, plus this residual vector. We can multiply this out, and the entire first term is deterministic, so it's not of interest here in this covariance function. So we can concentrate on only x transpose to the -1, x times epsilon transpose. And last time when we discussed the covariance matrix, we said that if I have the covariance of any matrix, let's say A times epsilon transpose, that this is the same as A times the covariance times A transpose. So it's just a repetition from last time. Using this result, I'm writing, so I'm pulling it out on the left-hand side. like so. And now here we had made the assumption that epsilon is IID, independent and identically distributed. So in other words, my covariance matrix is going to be diagonal, with a diagonal which is constant. And so I can just copy what's on the left-hand side, and I have my variance times the identity matrix, and I can copy what's on the right-hand side. But I can pull this scalar sigma squared out to the front, and then a few things cancel, and I'm left with sigma squared times x and x transpose to the -1. And that's the covariance of beta hat. So this is true for any distribution of my residuals, as long as they have an expectation of 0. Now we can make an even stronger assumption. We can assume that our residuals actually have a normal distribution. So if in addition we assume that epsilon I follow a normal distribution, so you remember the jargon, I wrote epsilon, then I wrote the tilde, meaning distributed according to the script n was a normal distribution, 0 was its mean, and sigma squared was its variance. So if in addition we assume that epsilon is distributed like so, then beta hat, which is just a linear function of epsilon, is also normally distributed. So then it also has a Gaussian distribution. Okay, sorry, my handwriting degrades. Normally distributed. Good. Let's draw a few pictures. So, are you done copying? One of the questions in the break was about these plots here. Yes, in these plots that I made, the dependent variable y points in the third direction. So it's pointing outwards. Yeah? So I have x1, x2, and y is pointing towards you. So these plots were meant to be three-dimensional, but when we discuss the well-posedness or not, actually the measured responses don't matter. The only thing that matters is what are the explanatory variables that I have in my system, or the explanatory measurements that I have in my system. Okay, I'm now going we can put it up there, but I'm copying it so we can sketch a little bit what my parameter estimates would look like in these three cases. So I'm getting out, let's say, beta 1 hat and beta 2 hat. My slopes in the first direction and the second direction. Now, the absolute value of what are these slopes I cannot discuss without having the measurements y available. So if, for example, you know, just to make something up, yeah? I could now draw isocontours of what do my observations y look like. Yeah? So here I have a linear increase of y towards the top right corner, let's say. Okay? So it would mean I have a positive slope of, let's say, +1, both on x1 and x2. So in other words, my parameter estimate for beta hat would look something like this. And now I can sketch the covariance structure. And the typical way to sketch the covariance structure is by using ellipses. And in this case here, I have equal, well, certitude on the slope in the first and in the second direction. So my covariance structure would look something like this. And if I do assume that my residuals are Gaussian, then actually this beta hat would follow a Gaussian distribution. And then what I've drawn here would truly be the isocontours of this isotropic Gaussian around beta hat. All right, let's draw the same kind of picture here. Beta 1 hat, beta 2 hat. Let's assume again that y increases linearly towards the top right corner. However, of course, you know, I don't have measurements everywhere. I have measurements only at these points here. Yeah? So, can you argue, you know, what my covariance structure will probably look like here? Yes?
Very sharp in one direction and the other.
Exactly. And in which direction is it sharp, and in which direction?
I would say the diagonal is broad and perpendicular, so diagonal normal, and in the other direction is
Let's have more voices on this.
The coefficient for x2 is unknown, basically, so the distribution has to be very broad and
Yes,
very narrow.
I agree. Yeah. So, and you might have said the right thing also. Yeah. So we can determine the slope along the horizontal direction very well. So we have a small uncertainty here, but it's really difficult to estimate the slope in the other direction, given how these points are located. So I have a large uncertainty in that direction. And well, if I'm again trying to sketch it with you know, elliptical contours, that's what it would look like. If my points were perfectly situated on a line, then these ellipses would actually be, you know, infinitely narrow. Yeah? So we would be completely undetermined along the second dimension. All right. Note again that, okay, so here I gave this blue example of what my response surface looks like. And I'm giving you a different response surface. Now I'm saying that, you know, I have a much steeper slope now. My contour lines are much more closely spaced, but it's pointing in a different direction. Okay, trick question. What will the distribution now look like? The same. Yeah. So the distribution that we find is independent of the measured responses. It only depends on the configuration of measured explanatory variables. Which is also why I could completely have omitted, you know, the blue lines just to make it a little more concrete. Yeah? So now, same story. Let's take the same linear increase of our response towards the top right corner. Let's hope that we find the same beta hat. I think we can guess that now this will be tilted somehow, but in which direction? We can think about it for a moment. Or discuss with your neighbor. So for me, it helps me if I look at this picture and if I think about the possible planes and to think about, in which way will the plane be stable and unstable. And then I look at the sets of parameters that I will find for the unstable planes. Any opinions? Yes?
And the variance in the direction of our data is small and in the orthogonal massage.
So you're saying the variance would be, I think you're saying this. Yes? Yeah. And I agree. So, unless I might be wrong, but my reasoning here was that if I look at where these measurements are, the plane will be poorly defined. How do I show this? In this direction here. So think of this as a hinge, and we now have a plane that we can turn around this hinge. There's the advantage of being in the lecture, not on the video, because you can see what I'm doing with the laser pointer. So, think of this as being a hinge, and now we turn around that hinge. Let me try and illustrate graphically. So I can have a couple of planes here that this plane, or let's say that plane, the planes are all a good fit to the data. They just meet along the measured points. So all of these planes are essentially possible given the measurements. And if I look at the slopes of these planes, either they both have a large positive slope in the x1, x2 direction, or they have a large negative, or they both have a negative slope. So this is why I now express this correlation. And so this is the kind of distributions we would expect for the configurations on the left, on the middle, and on the right-hand side. And okay, I've now been optimistic and assumed that we somehow have a distribution okay, I'm revising my plots very slightly and putting a star here. Yeah, so I'm saying that our distributions that we are bias free, so that our distributions are centered at the correct choice of parameters. And the choice of parameters that I used here now, of course, depends on the real measurement. So I'm now making this blue to say that these were the true parameters associated with these blue iso contours that I showed before. So as I go here from the blue to the red example, the B star will of course change, so my distribution will shift around in space, but the covariance structure will be the same. Okay, so for the blue example, I get, okay, let me color code this. For the blue surface, this is what I would find. And for the red surface, let's say it has a large slope in x2 and a smaller slope in x1. And now I need to say if it's positive or negative. I'm pretending that this is a negative slope in x2. So perhaps B star, the red B star would be located here, but it would have the identical covariance structure. Okay. Any questions for this? Yeah?
I'm not exactly sure what these blue and red lines mean.
Okay. What did the blue and the red lines mean? I tried to sketch the dependence of y on x1 and x2. So if you, these were isocontours. So if you look at the topographic map, if the topographic map tells us where mountains and valleys are by showing isocontours, so closed lines of equal height. And I've done the same here. Yeah? These lines being parallel, or I tried to draw them parallel, means that they're parallel and they're equidistant, which means I have a linear trend. What the sketch does not tell you in which direction is up and which is down. Here I meant that it increases towards the top right corner. So this is what blue and red here meant. Thanks for clarifying. Yeah.
What's the name of the plot that you see in the lower row?
What's the name of the plot? Manuel?
Just the plot of distribution.
It's the plot of the Bayesian would even like to say posterior distribution. Here we have not put a prior on it, but it's a plot of the distribution of my parameter estimates. I don't know a better name, I'm sorry.
Basically, you're just visualizing. We now have, if we assume this, the distribution of the P star is a Gaussian, and you're just plotting what a two-dimensional Gaussian would look like. There's no specific name.
So what we see is like the arrow on those axes?
Okay, let's concentrate on the middle example here. I'm first cleaning up the plot a little bit because there's too much going on here. All right. So the black points indicate where I have made measurements. The indicate how y depends on x1 and x2. This is the truth that I'm telling you. Yeah? So I'm telling you that y behaves like this. You will never know because you only know the measurements along the few black lines. Yeah? So the true slope along the x and along the x1 and x2 directions is both +1. Yeah? So I can, here at +1, know that this is my true parameter value, beta star. This is the vector with the two entries +1, +1. Now, this distribution tells me that if I have noise in my measurements, what are the values that I'm likely to actually estimate. And if the points are perfectly on a line, then this distribution here would be infinitely narrow. But to make things a bit less extreme, I'm not drawing these black points here perfectly on a line. I'm just saying they are, nearly on a line. Yeah? So beta star is the true slope that only the oracle knows. And now you give me a real set of measurements, and I'm trying to estimate what is the slope. And this distribution tells me what are the estimates that I'm likely to get. So I'm pretty likely to get this estimate, or that one, or that one, or that one. You see, they are not +1, but they're maybe plus 0.9 or plus 1.1 or so. These are the measurements that I'm likely to get. These are measurements which I'm very unlikely to get. Or these are estimates which I'm very unlikely to get. So these distributions tell you given a true parameter value, what are the ones that you're actually likely going to observe. Let me add another example, okay? Let me add a fourth example. X1, X2. It's related to the first example. I have measurements that are well spaced out in X1 and X2, but unfortunately they're all a little bit close together. Now, I'm still pretending that the true unknowns, or the true slope known only by the oracle, is +1, +1. Now, with regard to the first figure, the one on the very left, the true parameter is the same. Beta star has values of +1, +1. With regard to the first figure, is the uncertainty here going to be larger or smaller? The uncertainty is going to be larger because if I have finite measurement noise, if I have two measurements and I'm trying to estimate a slope, if these measurements are very close together and I have a little bit of noise, then my slope, it changes drastically. If I have the same amount of noise and my measurements are far apart, then my estimate will wiggle just a little bit. Yeah? So because these points are nicely spread in X1 and X2, I will again get an isotropic distribution, like on the left-hand side, but this time it will be much wider. So the isocontours here will indicate that this is a broader distribution. I hope that helps answer your question. Yes?
So the whole point of the second plot is that the data is correlated, right? That X1 and X2 are correlated.
Yes?
So in principle, I could explain my Y just with X1, for example.
Exactly.
Okay, but I could also explain it with X2. So what I don't get is why do I have a high uncertainty of one of the two parameters? If I could just take any of the two to explain my Y, why does one have a greater uncertainty than the other one?
So I think the best picture that my best explanation I already tried to draw, but I will try again. Hopefully the picture will come out a little bit more nicely. Yeah? So let me try a 3D picture this time. So we have x2, we have x1, we have y, and now we said that these measurements are anti-correlated. So the measurements were basically sitting here in the plane, and now I can invent some measurements, just because I'm making a 3D plot here, just for sake of completeness. And I think we can see that, let me make it more extreme. I here have, so as I go to the front, the values of y are growing. Okay? So towards you, I observe larger values of y than at the back. Yeah? And now, imagine, so now I want to fit a two-dimensional plane to these measurements. And my plane will be well supported along what now to us is the front to back direction. It will be poorly supported in the other direction. And hence I must have a parabola which is narrow in the one direction and wide in the other. Now, along which dimension? I think that's easier to understand actually in the third plot, because here in this third plot, it's clear that I have a good support along the first dimension. I'm going to be able to estimate the slope reliably in this direction and very unreliable in the other direction. Yes, I think this plot here makes sense. And the other one here is just a rotation of it. Yes?
What is the difference between beta and beta hat?
Okay. So partly, my notation has been a little bit sloppy. Huh? The statistical model says that we have, so first of all, we assume that the linear model actually holds. And then this has some true unknown parameter beta star. Then we have some measurements y, which are a combination of, on the one hand, the true linear trend, and on the other hand, this random noise epsilon. And given y and given x, we estimate the parameters, and I call this parameter beta hat. Yeah? And now in between, when we were deriving the equations, we had a few betas which had neither a star nor a hat. Yeah? So these equations here. And this I wrote, for these equations here, I don't need a probabilistic interpretation. I just say that I define this to be my sum of squares, find the beta which will minimize this. And so in these lines here, I put neither a star nor a hat. But then when I say what's my parameter estimate in this equation here, now it would be legitimate to put a hat on this and say this is my best estimate.
So plugging in y hat here will give me the beta hat, right?
No, plugging in the y will give me the beta hat, and plugging in the y hat, that's my prediction. Yeah, it coincides. That would not, So we do plug in the y because we want to find the beta hat, and once we have the beta hat, we can get the y hat. The y hat is the prediction at the locations where we have measurements. All right. On a final note, I want to say that one of the cases when this breaks down is when we have outliers in our data. So if we have single measurements of y that are just completely wrong, that don't follow the ordinary distribution of residuals, then we will get a really wrong estimate. It can be arbitrarily wrong. And this is why on real data, we might have to use not just minimize the sum of squares, but we might have to use a robust statistic and use something called a robust regression. The advantage is it becomes immune to outliers. The disadvantage is you need to specify some parameter to say just how robust do you want to be. And the big advantage is that it can no longer be solved in closed form. So here we had to solve a system of linear equations to find our parameter estimate beta hat, and that's very simple, closed form. We get a unique solution. And if we turn to robust regression, this is a non-convex optimization problem, and well, optimization of that becomes harder. Next week, we will revisit this problem of the ill-posedness and discuss how we can amend it using two really important regularization techniques. Have a good time. See you on Wednesday.